In the vast, silent theater of the cosmos, there are places where stars go to die, places where light itself is captured and can never escape. These are not just empty voids, they are the universe's most extreme creations, an endpoint for matter and a frontier for our understanding. They are gravity's ultimate triumph. For centuries, we looked to the heavens and saw only light, but the greatest secrets of the universe are kept in the dark. These are cosmic ghosts, regions of space-time so warped, so violent, that they defy our imagination. They are, of course, black holes, and their story is the most dramatic tale the universe has ever told. It's a story of life, a spectacular death, and an eternal, mysterious afterlife that shapes the cosmos itself. So, what is a black hole? Forget the image of a cosmic vacuum cleaner. It is far stranger. Imagine taking a star 10 times more massive than our sun and crushing it down into a space smaller than a city. The result is an object with a gravitational field so intense it becomes a prison for everything, including light, the fastest thing in the universe. This isn't science fiction. It's the natural, albeit terrifying, consequence of gravity. A black hole is a one-way door in the universe. Once you pass its threshold, all paths lead to one place, the center. It represents the final victory of gravity over all other forces of nature, creating a permanent scar on the very fabric of space and time. Every black hole begins with a life of brilliant intensity. Our story starts with a star, not an ordinary star like our sun, but a true titan of the cosmos, more than 20 times its mass. For millions of years, this stellar giant wages a constant war with itself. In its core, a furious nuclear furnace fuses elements, creating immense outward pressure. This pressure is perfectly balanced by the relentless inward crush of its own gravity. This delicate dance of forces is what allows the star to shine, to burn with a light that can be seen across galaxies. But this celestial balancing act cannot last forever. Like all stars, this giant has a finite amount of fuel, and the clock is ticking towards a truly spectacular end. When a massive star exhausts its nuclear fuel, the war against gravity is lost. The outward pressure from fusion ceases, and in less than a second, the core collapses under its own colossal weight. This catastrophic implosion triggers a rebound shockwave, creating the most powerful explosion in the universe, a supernova. The star's outer layers are blasted into space with unimaginable force in a final defiant scream of light that can outshine its entire galaxy for weeks. It's the universe's greatest firework display, seeding the cosmos with the heavy elements necessary for planets and for life. But while the star's ghost expands into space, its heart, its core, continues to collapse, destined for an even stranger fate. If the remnant core left behind by the supernova is massive enough, roughly 3 times the mass of our sun, no force in nature can stop its collapse. It crushes itself past the density of an atom, past the density of a neutron star, shrinking relentlessly. As the core gets smaller and denser, its gravitational pull becomes exponentially stronger. Space-time itself begins to wrap around it like a shroud. At a critical point, the escape velocity from the core's surface surpasses the speed of light. At that instant, a boundary is forged, an invisible membrane called the event horizon. From this moment on, the object is sealed off from the rest of the universe. A new black hole has been born, and the darkness is absolute. Let's journey inside. At the very center of every black hole, our current understanding of physics shatters. Here lies the singularity. It is a point of zero volume and theoretically infinite density. All the mass of the collapsed star and everything that has ever fallen into the black hole is crushed into this single dimensionless point. Here gravity becomes infinite. Time and space as we know them cease to have meaning. It's a place where the laws of general relativity and quantum mechanics, the 2 pillars of modern physics, collide, and we have no theory to describe what truly happens. The singularity is the ultimate unknown, a cosmic mystery locked forever behind a wall of absolute darkness. Surrounding the singularity is the black hole's most famous feature, the event horizon. It's crucial to understand this is not a physical surface. You wouldn't crash into it. It is an invisible spherical boundary in space-time, a border defining the region of no escape. Think of it as the edge of a cosmic waterfall. far away from the edge. You have the power to steer away, but the closer you get, the faster space-time itself flows inward. The event horizon is the point where that flow exceeds the speed of light. The moment anything crosses it, a planet, a star, a particle of light, it is caught in the current and dragged inevitably towards the singularity. There is no turning back. Black holes don't just pull things in, they fundamentally alter the reality around them. According to Einstein, massive objects bend the fabric of space-time. A black hole does this to an extreme degree. As light from a distant star or galaxy passes near a black hole, its path is bent, as if passing through a powerful, invisible lens. This phenomenon, called gravitational lensing, is one of the key ways we can detect these invisible objects. From our perspective on Earth, it can create bizarre and beautiful effects. We might see multiple images of the same galaxy, or light from a distant star distorted into a perfect circle known as an Einstein ring. The black hole acts as a cosmic magnifying glass, revealing its presence by warping the light of the universe. So, what would you see if you decided to take the ultimate plunge and fall into a black hole? The journey would be the most surreal experience imaginable. As you approached, the black hole would fill your vision, a perfect circle of blackness against a strangely distorted universe. The light from stars behind it would be bent and warped into a bright ring. As you got closer, you'd notice something strange about time itself. To a friend watching safely from a distance, your fall would appear to slow down, getting redder and dimmer as you approached the event horizon, until you seemed to freeze in time, eventually fading from view. But for you, your own clock would tick normally as you prepared to cross the threshold. As you fall deeper into the black hole's gravity well, you'd encounter a truly gruesome force known as tidal gravity. Because the singularity is a single point, the gravitational pull on the part of your body closer to it would be immensely stronger than the pull on the part farther away. For example, the gravity at your feet would be thousands of times stronger than the gravity at your head. This differential would stretch your body, pulling you apart like spaghetti. This process, scientifically termed spaghettification, is the inevitable fate of any object falling into a stellar mass black hole. You would be elongated into a thin stream of atoms, flowing into the singularity long before you ever reached it. Gravity's most profound effect is not on space, but on time. This is called time dilation. The stronger the gravity, the slower time flows. Near a black hole, this isn't a subtle effect, it's extreme. If you could somehow survive and orbit just outside the event horizon for what feels like 1 hour to you, you could return to your spaceship far away to find that decades, or even centuries, have passed for your crew. The black hole is a natural time machine, but it's a one-way trip into the future. It demonstrates that time is not a constant, universal clock ticking at the same rate for everyone. Rather, it is a flexible, flowing river that can be bent and slowed by the immense power of gravity. Not all black holes are born from the death of a single star. At the heart of nearly every large galaxy, including our own Milky Way, there is a different class of monster altogether, a supermassive black hole. These are the true titans of the cosmos, weighing millions or even billions of times the mass of our sun. They are the gravitational anchors around which entire galaxies revolve. Their origins are one of the biggest puzzles in astrophysics. Were they born from the collapse of colossal clouds of gas in the early universe, or did they start small and grow to their immense size over billions of years by feasting on a constant diet of stars, gas, and other black holes? At the center of our own Milky Way galaxy, 26,000 light-years from Earth, lies Sagittarius A star. This is our supermassive black hole. It is a beast 4 million times the mass of our sun, confined within a space smaller than the orbit of Mercury. We cannot see it, of course. The galactic core is a chaotic, crowded place, shrouded by thick clouds of gas and dust, but we can see its undeniable influence. For decades, astronomers have tracked the motions of the stars closest to it. We have watched them whip around an invisible point at incredible speeds, some reaching millions of miles per hour as they execute their orbits. Their frantic dance is the smoking gun evidence for the monster that lurks in the heart of our galaxy. Supermassive black holes are not just passive objects. They are active engines that shape the evolution of their host galaxies. As gas, dust, and stars are pulled towards the black hole, they don't fall straight in. Instead, they form a vast, swirling structure called an accretion disk. The friction and pressure within this disk heat the material to millions of degrees, causing it to shine more brightly than all the stars in the galaxy combined. This is a quasar, the most luminous object in the universe. In some cases, powerful magnetic fields can funnel some of this energy into colossal jets of plasma that are ejected from the black hole's poles at nearly the speed of light, traveling for thousands of light years. For all of human history, black holes were purely theoretical, an extreme prediction of Einstein's equations. We could infer their existence, but we had never truly seen one. That all changed in 2019. The Event Horizon Telescope, a global network of radio telescopes working together as a single Earth-sized observatory, achieved the impossible. It captured the first ever direct image of a black hole's silhouette. The image was of the supermassive black hole at the center of the M87 galaxy. We saw a ring of fire, the superheated plasma of its accretion disk, surrounding a perfect circle of darkness. For the first time, we had visual proof. We had stared into the abyss, and the abyss had revealed its shadow. The idea that black holes could be gateways or wormholes to other places in the universe, or even other universes entirely, is a captivating staple of science fiction. The mathematics of general relativity does allow for such possibilities, known as Einstein-Rosen bridges. However, according to our current understanding, these cosmic shortcuts would be incredibly unstable and would collapse the instant anything tried to pass through them. Furthermore, the journey to the singularity inside a real black hole would be a one-way, destructive trip. While the idea remains tantalizing, and physics at the singularity is unknown, for now, the evidence suggests a black hole is not a doorway, but a final destination. For decades, a central rule of black holes was that nothing that falls in can ever come out. But in the 1970s, Stephen Hawking combined general relativity with quantum mechanics and discovered something extraordinary. He theorized that, due to subtle quantum effects at the event horizon, black holes are not completely black. They should emit a faint trickle of particles, now known as Hawking radiation. This means black holes have a temperature and, over immense periods of time, they can slowly lose mass and evaporate. This idea created a paradox. If a black hole evaporates, what happens to the information of everything that fell inside? Physics says information can never be destroyed, and this remains one of the deepest unsolved problems in science. The process of black hole evaporation is unbelievably slow. For a black hole the mass of our sun, it would take 10 to the power of 67 years to disappear, a number so vastly larger than the current age of the universe that it is almost meaningless. But it does imply that black holes are not eternal prisons. In the far desolate future of the cosmos, long after the last stars have burned out and the galaxies have faded, the black holes themselves will begin to decay. They will slowly radiate away their mass, shrinking over trillions upon trillions of eons. In the final moments of their existence, they will vanish in a final, brilliant flash of gamma rays, leaving behind an empty, silent universe. Black holes represent more than just cosmic oddities. They are the ultimate laboratory for testing the limits of our knowledge. They are the place where our two best theories of the universe, general relativity for the very large and quantum mechanics for the very small, must finally meet. To truly understand what happens inside a black hole, we need a new theory, a theory of quantum gravity, often called the theory of everything. Solving the mysteries of the singularity and the information paradox might be the key to unlocking this next great leap in human understanding. They are a physical embodiment of the boundary between what we know and what remains profoundly, tantalizingly unknown. From the death of a star to the heart of a galaxy, black holes are not just agents of destruction. They are fundamental architects of the cosmos. They govern the orbits of stars, regulate the growth of galaxies, and forge the elements from which we are made in their supernova births. They are a profound reminder that we live in a universe that is far stranger, more violent, and more magnificent than we can possibly imagine. They challenge us to be curious, to ask bold questions, and to keep pushing the boundaries of exploration. Because by studying these enigmatic objects, we learn not only about the universe, but about our own place within its grand, cosmic, and beautiful darkness.